So what we are going to do here at the very beginning of this script is just making sure that what I've talked about is really the case for real data. So we look at the Alberta Josem data set again, do some data processing to begin with. This is nothing new, just to create some extra covariate that we can use later on. And then just take the counts, just vocal observation, sorry, not visual, that means vocal observations only. And what I'm also going to add as a column is this duration and distance information combined together. So now we know which counts are coming from 0 to 3 minute and 0 to 50 meter combined bins. And some of them are coming from 5 to 10 minutes and 100 plus. And once we have this, then we can create this cross tab. As you recall, we are going to count the number of rows for each site and this combined duration distance bins. And then species ID, that is just going to replicate this over multiple species. So we'll have a list of matrices where site ID is going to be the row name, and these labels are going to be our column names. And it's already done. So now what we can do, pick a species, extract this matrix for that given species, and turn it into a real matrix so that we don't have to look at sparse matrices. So this is what it looks like. We have a breakdown of the counts in these various bins of combinations of distances and time intervals. And now I'm going to create the totals as if those were different methodologies. But remember, this is all the same studies, same observations. So if I take these different subsets, the true abundance that was there is the same. If you happen to just observe for 3 minutes or 10 minutes, that is not expected to change the true density. It is going to influence the counts. So what we expect here is we have these 9 combinations of 3, 5, 10 slash, sorry, yes, 9. So 3, 5, 10 slash 50, 100, and infinity. And so we combine together all the counts. So we get this kind of difference across the means. As the area increases, we get higher counts. But you can see within the same area sampled with increasing time, you get higher counts for the species, and feel free to pick a different one as we did before. So this is what we are going to use as just pretending to be different methods. And we want to see if by adjusting for the methodology using the techniques we've learned in the past 2 days, are we going to get the same answers or not? And we expect that this should work. So let's see if that's really the case. And this was just the total count. Now we can take those subsets to fit the removal modeling, which is the usual thing. We are just using the duration intervals. So this is kind of independent from the previous data processing, but we'll come back to that. So this is what we did on day 2. This is how we fit removal sampling using the time interval data. So we have the counts in these time intervals, which are not cumulative, but just new individuals in the new interval. We have the corresponding D matrix saying 3, 5, 10 minutes, and then the summary of this model with a day effect. So then estimating phi, we use the coefficients and this model matrix, exponentiate, because as the coefficient says, it's on the log scale. So we get these values for phi. Not a large variation, but it varies from 0.4 to 0.45. We do the same for distance sampling, and I'm not doing any kind of model selection here, just kind of, I recall that these worked good in the past using day as a fixed effect or habitat for this tau distance sampling component. So if I run this as well, it's the similar idea, but instead of removal sampling, now we specify distance sampling, and also our data corresponds to the increasing distance bins. Okay, it's done. So head of y this 0 to 50, 50 to 100, 100 and beyond. Corresponding d 50 meter, that's 50 divided by 100.5, 1 and infinity. These are the endpoints we need to provide. And then the summary of m this. We used habitat, which was a categorical variable. So we know the intercept, which was the open habitat. And then we have our fixed effect estimate for deciduous and coniferous forests relative to the open habitat. So we can use, again, this line to estimate our tau, which is the model matrix from the distance sampling model and the coefficients exponentiated, and we get this summary. It varies from 68 meters to 74 meters, depending on habitat type. Because again, the interpretation for tau with the half normal, which is what we imply by fitting this particular distance sampling model, is that this estimate is going to be our effective detection radius. So now let's see how we can calculate the offsets corresponding to those different methodologies. Again, 3-minute 50 meter, 5-minute 50 meter, and so on. So let's just create these two functions so that we don't have to look at ugly formulas all the time. The nice thing about R is that you can just put everything you don't want to see into a function and call that function, and it looks much nicer. So it's like saying f of y, and you can see p fun of 3 and phi instead of 1 minus e to the power minus t times phi. Even just saying this takes longer. So if I were to read this out loud, we would be sitting here 4 hours later. So let's just skip that. We have these two functions, p and q, and you can look this up, why we need to calculate it this way. But trust me, this is going to give you the right quantity under the exponential removal sampling and half normal detection function. So our availability using the same phi, so the only thing that is changing here is the total time. So if you remember that cumulative density function is smaller at 3 minutes, then it increases further to 5 minutes and to 10 minutes. So that's the only thing what's different here, and we get this P3, P5, P10. So the relative ordering of these are going to be the same, but the means are different. So if I look at summary P3, then it's 0.7, 0.74. If I look at P10, that is very close to 1. So now we are reaching that asymptote of the cumulative density function. Now the average detection refers to the pi dough in 3D, right? And the gigantic cookie cutter, and then the dough compared to the volume of the cookie cutter. So this is what we get for 50 meter, 100 meter. This is the known area that we've sampled. average detection within that area is going to be a function of this tau that we estimated, and this varies from location to location depending on what the land cover type is, same way as phi varied from survey to survey depending on which time of the year it happened. And as a result, our Q values are going to be a function of tau, which is a function of land cover, plus the area. And for the unlimited portion, we need to calculate the effective area, which is tau squared times p. And for the known area, we need to calculate also the area, which is 50 meters squared times p or 100 meters squared times p. So let's do this. And now we can calculate the corrections, which is everything else besides d in QPAD. So a times p times q with the corresponding values. 50 meter, 3 minute, 50 meter, and so on. So up to this point, it's nothing surprising. So you can just multiply together a times p times q, watching that the differences are lining up well. So here you have 5 minute, 5 minute, 10, 10, okay. 100, 100, 100, looks good. So for the infinite, you see 3, 5, 10 minute, 3, 5, 10 minute, good. Q, we just use 1. This is here so that we don't forget what we are doing. It just kind of yells at us that this is unlimited. And then EA, which is the effective area sampled, is used here. So now we have this matrix, which is going to match our YC matrix. So this was the combined one where we had the counts for these pretend protocols. And now we have this correction matrix, same dimensions, same headings. So now we have the counts and the corresponding corrections. Now we can look at how these corrections change with protocol. And this is another little bar graph to see that yes, these correction factors increase with time and increase with area. So as you recall, there was a similar pattern for the counts. So if the pattern is similar, that just means if you divide one with the other, you get kind of the same number. Let's see if that's the case. Again, recap here, how we calculate density, mean count divided by the correction. Let's do that and see if that's really more or less the same. So I'm using 10-minute unlimited as the reference. That's the horizontal line. And you can see there is some variation, much less for larger area when the counts are more similar. And for 3-minute and the smallest area, you get a bit more variation around this line. But given this is one species, not a overly huge data set, this is still okay. And so this difference is coming from smaller time and distance sampled. That means less number of counts, and it leads to more variation. And this is what we can see here. And now let's do this in a GLM framework and without explaining this too much. So this is just fitting the same model to each of these columns as the response variable using deciduous cover as our predictor and no offsets. So just plain GLM. This is what we would do naively with the different protocols. You can see these coefficients that the fixed effect is not changing a lot. There's some difference, again, for these smaller counts here, 3, 5 minute, 50 meter. But here you see 2.2, 2.1, very close. But the intercept, that's where you see lots of differences. So if we were to make a density estimate from this, kind of just looking at the mean of the fitted values, we see the same pattern. They're all the same. And if you go out with this protocol, you are going to say relative abundance is 0.2. If you go out with this protocol, you might say 5 times higher. So you can't really tell if this is abundance or relative abundance. You can just say, if you have a deciduous forest, it's going to be this much higher, which, as you can see here, is still working no matter which protocol you use. But if you have multiple protocols, then it might come into play and you want to account for that. So if it's single protocol and you're interested in relative abundance, maybe you don't need to do any kind of correction. If you have different protocols or you want to talk about real density, then you need to take these into account. So let's clear up what do we mean by an offset. So in colloquial terms, we have an offset which just sets off something up and down. So that's like a simple addition. You add something to an otherwise estimated value. So this offset is a known quantity. You add it to the mean and it goes up and down. And because it's additive, it is also, for our purposes, it's going to be on the log scale. So the log of the correction, which is A times B times Q, is going to be the offset. And I use the index I so that we can refer to survey I. And we have n surveys. So I goes 1, 2, 3, 4, ... n. So for each survey, we can come up with a correction value, which we can turn into an offset. So when I talk about offset, I mean corrections on the log scale, because this is what we use in our log linear modeling. Like here in the GLM, same idea. We calculate the log of this correction matrix. So we have columns for each of the protocol, and we are going to then take a corresponding column from the counts matrix and the corresponding column from the offsets matrix and fit the same GLM as what we did before. Now, if you look at the coefficients, not only the fixed effect, but also the intercepts are much more similar. So we are getting somewhere. This offset thing is really making things more comparable across the different protocol types. So now what we do here, just create a model matrix, because we are going to use that later on for fitting different models. And then just calculate the mean prediction this way so that we can make sure the offset is not going to get incorporated. DO, density with offset, you can see these mean values are much more similar, and with the bar plot, now we see a very interesting pattern that mimics of what we did just using the mean counts. So kind of that division was very similar to this, but now we were able to talk about the whole regression thing, so we can now visualize how density is changing with the amount of deciduous forest in the neighborhood. So you can see from this graph that we are getting very similar answers no matter which protocol you use. So now we can mix and match together different protocols, use these ideas, and talk about the same quantity without having to deal with all kinds of fixed effects for the methods, and still figuring out which should be the reference and whether this means density or not. So we are getting closer to that true value that we cannot directly observe, but we are very interested in. So now, to finish this before the break, let's just make the prediction for the naive GLM. That's going to be our fit one, and the offset included GLM, which is our fit to, and then plot it. This just means these are the relationships with deciduous forest amount, and this is what we get on the same kind of y-axis scale. For the naive GLM, you can see here, this is the 3-minute, 50 meter is the black. So when you do 50 meter based analysis, time comes into the picture slightly, but it's more about the area sampled, and this just reflects differences across the counts. If you do 50 meter based survey, you can still say that if it's fully forested, you're going to get 3 times higher expected abundance when it is not forested, or maybe higher. And that is probably the same if you look at the 100 and infinite unlimited counts. So going from 0.3 to 2.5, kind of that relative difference might be very similar, but the absolute numbers are going to be vastly different across the protocols. Now, when we use the offsets, everything is kind of in the same region. So not just the relative differences, but the absolute values are going to be much more closer to each other. So based on this, we can conclude that offsets are really working when you need to account for differences in methodologies. So let's have a quick break. And then after that, we are going to look at, now once we have the offset and we know, yes, it is working, how can we fit different kinds of regression models? And that is one piece that we skipped on day one. So kind of circling back to that and covering it a bit more is going to be helpful, because this is what you would need if you want to do your own modeling and you have an idea about, okay, I remember we did this GLMM, let's just see how to include an offset and how to make a prediction.